sulfonic acids. Under this heading, we are going to discuss introduction of sulfuric acid and sulfonic acid and preparation. Sulfonic acid. So sulfonic acids are less common than carboxylic acid. They are not much more popular, but still they are creating a very important class of organic compounds. Their general structure is RSO3H, and the most widely used sulfonic acid is para-toluene sulfonic acid. Very popular, particularly in drugs. So very popular para-toluene sulfonic acid. Its general formula is RSO3H. So when we expand that general formula, we can write the general formula like this, RSO3H. So on each oxygen there are two lone pairs of electron, and as I mentioned earlier, the most popular, most widely used sulfonic acid is para-toluene sulfonic acid, which is abbreviated as TSOH, which is also called tosic acid. So you remember this name, tosic acid. Now the sulfuric acids are very strong acids, very strong acid. You can check its pKa value, it's in minus, negative. So because of that, it is very strong. Why it is strong? Because we know very well, we have seen before this. So whatever anion is produced by the removal of proton, if that anion is, or you may call it as a conjugate base, if that conjugate base or anion is more stable, then the acid is more stronger. But in general, stronger acids having a weaker conjugate base. So because of that, why this is weaker? Because this anion is stabilized. You can see here 3 resonating structures you can draw for its anion. But in case of carboxylic acid, we can draw only 2 resonating structures. So as compared to that, this anion is more stable. You can draw. This pair is coming here, so the double bond will generate here, and one pair of this pi bond will move on the oxygen in the next structure. So the negative charge is migrated from this oxygen to this oxygen. Now this pair will move in between oxygen and sulfur to form a pi bond, and to accommodate that pi bond, this pi bond will move on the oxygen. So in next structure there will be 3 lone pairs. So the negative charge is now moving from this oxygen to this oxygen. So actually this is unstable because of negative charge, but this negative charge is distributed among 3 oxygen. So each oxygen now carrying 1/3 negative charge. Obviously this is less than 1. So because of that, this is more stable. So because of this acid becomes stronger, but this base means this conjugate base becomes a weaker base. Because of this property, this group is now you will see in the next or forthcoming videos that this group is a very good living group. Now we are going to discuss preparation of benzene sulfonic acid. So we'll discuss first how benzene sulfonic acid is prepared. It is prepared by this sulfonation reaction. So this reaction is called sulfonation reaction. This reaction is called sulfonation reaction, and this is electrophilic substitution reaction. So this is electrophilic substitution reaction. So you remember these 2 words. First, it is sulfonation reaction. Second, it is electrophilic substitution reaction. So for this purpose, we have taken benzene and we have added H2SO4 and SO3. So this mixture is called oleum. Sometimes it is also written as H2S2O7, oleum. Now, in presence of this, even at room temperature, sulfonation takes place and we get here benzene sulfonic acid. So benzene, this is sulfonic acid functional group. So benzene sulfonic acid is produced. Now we are going to discuss its mechanism. So as I mentioned earlier, it is electrophilic substitution reaction. So I'll write here SO3. First of all, the reaction between SO3 sulfur trioxide and H2SO4. So you can write SO3 this way. On each oxygen there are two lone pairs of electron and having double bond with the sulfur. Now it is acid-base reaction between these two. So proton is donated from H2SO4 acting as acid and it is acting as a base. So proton is taken by using any one of the oxygens you can select. I have selected this one. Actually, this is taking place like this. This is taking place like this. So the lone pair is given. So the positive charge is developed on oxygen. But very soon, this will take its lone pair back from this pi bond and we get here this sulfur and H. Now two lone pairs here and positive charge is migrated from oxygen to sulfur because it is more stable. So I have written here this intermediate electrophile form after the acid-base reaction between SO3, sulfur trioxide and H2SO4. So this electrophile is generated and one proton is donated from this H2SO4, we get these anion. So this positive and negative ion pair. Now once electrophile is generated, these two steps are actually we have seen many times during electrophilic substitution reactions. So when this electrophile attacks benzene ring because of pi electrons, so you have to remove any one of these three pi bonds outside. So this pi bond I have selected. I'll give a different color. So you can remove this pi bond either here or here because it is in between these two carbons. So you have to remove this outside as I mentioned earlier. This is removed here and now the electrophile getting a pair of electron to form bond between this carbon and sulfur. So this carbon and sulfur. Now something is missing here at this carbon. There is a proton, but still this carbon having 3 electrons and means 1 electron less. So because of this, this carbocation is generated. So this carbocation can undergo resonance or it is stabilized by resonance by just shifting this adjacent pi bond, which I have shown by using this curved arrow. So if I shift this pi bond here, means here, a similar kind of structure will develop here. That means this positive charge will migrate from this carbon to this carbon. In next structure, you have to move this pi bond by using this curved arrow. You can show. Now this is coming here in between these two carbons. So this is newly shifted pi bond. A similar kind of structure will develop here at this carbon. So the positive charge is migrated from this carbon to this carbon. So in this way, for this carbocation, we can draw 3 resonating structure. That means it is stabilized. So once that electrophile is attacked and carbocation is formed, so third step, in fact second step, is removal of proton. So this step is a fast step because this will try to remove this proton as early as possible, because while doing so we get this aromatic ring back, and the aromatic ring back means stability back. So stability is gained because of this aromatic center. So because of that, this proton is removed as early as possible. So this anion is generated in the reaction mixture, will take up this proton and the bond in between this carbon and proton now moving inside as a pi bond. So this pi bond is generated here and we get our aromatic center back, and this HSO4 now becoming H2SO4. In this way, by using this oleum, you can produce benzene sulfonic acid, and if there is another substituent present on the benzene ring, so we have to consider their directive influences, ortho-para directing group, will direct this electrophile towards ortho and para position. In that case, we'll get two products. And if meta-directing group is there, that group will direct incoming electrophile towards meta position. So in this way, we can write a sulfonation reaction for substituted benzene ring. Thank you.